Good evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to How the Weather Works training series. This is video part 9. And in today's video, I'm going to be continuing on a discussion that I started the last video in part 8. I talked about polar front theory, some of the involvement of how a cyclone at the surface develops. I did hint in the last video of how the surface is connected to the upper levels of the atmosphere. For example, on this particular image to start tonight's training presentation, we're looking at a long wave pattern in general with a long wave trough, and we have these little areas of disturbances within the long wave trough. These are known as short waves, and I covered the characteristics of both short waves as well as long waves in the last training video to kind of introduce what those waves specifically meant for us. So let's go ahead and get right into the video. Tonight's training covering pretty much the three-dimensional aspect of pressure systems. All right, so let's first talk about upper air support features, and these are very important in order for surface highs and surface low pressure areas to really either weaken or strengthen. We first talk about cyclogenesis with an area of low pressure at the surface. Cyclogenesis referring to the development of a low pressure system at the surface or a strengthening of that system. We have to look how the surface and upper air events or those upper air features are linked. Of course, we're used to seeing the weather here at the surface of the Earth where we live. However, upper level support in the form of the short waves, for example, the mid levels of the atmosphere, those areas of upper level divergence aloft, the jet streaks up at the 300 millibar level, those all work together in unison to create storm systems, mid-latitude cyclones. So these long and short waves in general can cause, promote, or suppress that wave formation at the surface. And that's the important thing to remember. And then in turn, that surface cyclonic shear, as I discussed in the last video when I talked about polar front theory, can produce these temperature advection or thermal advection patterns where warm air moves towards the north, colder air to the south, and you get the turning of the air masses and the turning of the winds inward towards the low pressure across warm and cold fronts. And overall, what happens when you increase surface cyclonic shear, it can produce that temperature or thermal advection that ultimately alters the upper air pattern, the jet stream flow as the main consideration, as well as these short waves in the mid levels of the atmosphere. And we'll get more into that here in a minute. So at that 500 millibar level at about 18,000 feet above the ground where we live, short waves exist or form above surface stationary fronts. Now, when I went to meteorology school, there was something known as Pedersen's rule. And Pedersen's rule simply stated is an area of upper level divergence associated with a shortwave trough superimposes itself upon a low level frontal boundary, and eventually that kicks off the development of a surface low pressure system. You increase low level convergence that leads to upward vertical motion, and then you get, as that divergence comes across over the top of that surface low, over that frontal boundary into the surface low that's developed, it's going to result in a strengthening surface low. In addition to that divergence, we have positive vorticity advection, an area of positive vorticity that moves in over that surface low. All these factors come together to actually produce upper air waves with cyclonic flow that is going to supplement the cyclonic shear or that cyclonic turning of the winds at the surface, supporting or initiating the cyclonic flow about a surface stationary front, and you get that development of that surface wave. In the initial phase, the upper air wave, that short wave aloft, is going to deepen or strengthen, forming an area of convergence upstream of the trough and an area of divergence downstream of the trough. Now let me draw out what that means here. Okay, get to the tool here. Okay, so when we talk about upstream and downstream, of the trough, I want to just denote what that looks like. So if this is, let's say this is your trough, okay? This is your trough axis, okay? Areas that are considered downstream from the trough axis, this solid line, are going to be located in this position. This is considered, that's going to be considered downstream of the trough axis. This is going to be considered upstream. All right, so in the northern hemisphere, in the mid latitudes, when we talk about troughs, when we're out ahead of a trough or to the east of the trough axis, that's an area where you're typically going to find that area of divergence downstream. And then the upper level convergence is going to occur upstream, which is in this location right here. Okay? So just wanted to show you the reference points. So we typically have divergence downstream of the trough axis, convergence, air converging the upper levels of the atmosphere, upstream of the trough axis. So as this trough axis passes over your area, let's say over a particular city in the United States or in Europe, generally the divergent area and positive vorticity is going to be ahead of the shortwave trough axis, and that negative vorticity and convergence is going to be behind the trough axis. So once the trough axis passes your location, let's say it's moving west to east, generally you're going to have stormy weather associated downstream of the trough axis, and you're going to have fair weather upstream of the trough axis associated with the upper level convergence. And that's the very important part of all of this. So the area of upper level divergence represents a favored location for the continued development of a surface low pressure system that encourages synoptic scale chimney effects. And I talked about the chimney effect in an earlier video, but basically what it is, if this is the surface here, this red line, these arrows represent low level convergence at the surface. Okay, see how they're coming together like that? So as the air meets and converges in the low levels, it must go up. All right, and then as it goes up, eventually what happens is it spreads out and diverges. This is the upper level divergence aloft. This is the chimney effect. Low level convergence, upward vertical motion, and then upper level divergence over that low level convergence. That's a chimney effect. We're removing mass aloft over this air column, over this area of low pressure. Typically you have low pressure here at the surface. Okay. With the surface low developing downstream of that upper air trough, the vertical axis of the low pressure center will begin to slant or tilt toward the colder air with height. Now, let me talk to you a little bit about tilts. There's different types of tilts that we see. I'm going to go ahead and draw them out right here in the bottom right-hand portion of the slide. This is an example of a negatively tilted trough. One that has a trough axis that extends from northwest to southeast. Now, negatively tilted troughs are associated with some of the most intense cyclones in the mid-latitudes. Okay? We have accelerated area of divergence out ahead of the trough axis. We just have really good dynamics overall. When we have a negatively tilted trough, we have a very mature cyclone. Some of the stronger storm systems you will see are associated with negatively tilted troughs. Upper level features, a short wave is digging into the long wave pattern, and we're just really getting things going. The timing is really great. Location, the features is just really good too to develop a really strong storm system. That's a negative tilt. Now, if you just have a tilt like this, let's just say that U shape there represents a trough and it's just pretty much north to south like this, that is an example of a neutral tilt. And then a positive tilt is going to be one that's generally located, it's going to have a trough axis that extends from northeast to southwest. That's a positive tilt. Okay. This one in the middle again represents neutral. I'm just going to put an N there, and then this is a negative tilt. Okay. So the strongest storm systems are associated with these negative tilted troughs. If the divergence aloft, and let me go ahead and remove this. Let me erase this stuff here. So just wanted to show you a couple of things here drawn out to enhance the training. All right, so let me go back to this. Okay, so if the divergence aloft intensifies, the chimney effect is going to grow stronger, and it's going to promote increased low-level or surface converging of air, and that's further going to intensify that surface low pressure. So what we're getting at again here, I probably should have just left this up. Here's the surface again, okay? You have low-level convergence. These are the arrows coming together here on the surface of the Earth. As the air converges, it rises in the vertical, and usually when air rises in the vertical, it cools and condenses and forms clouds and precipitation. And then you have upper-level divergence over this air column. Again, I'm showing you an example of the chimney effect. Now, what happens if the upper-level divergence, this location here, the upper-level divergence is greater or stronger than the low-level convergence? So I'm removing more mass aloft. I'm moving that mass aloft at a much quicker or accelerated rate at the top of the air column. That's going to result in increased low-level convergence here at the surface. This really happens, especially in like tropical cyclones, when they really intensify rapidly. When they go from, let's say, a Category 2 hurricane to a Category 4 in a matter of 12 hours. All right. This also happens when we talk about mid-latitude cyclones and bombs that form in mid-latitudes where you have a 24 millibar pressure drop in 24 hours. Just explosive, rapid development in these low-pressure systems. When you have this upper part of the storm where you have upper-level divergence, removal of mass, I'm putting a plus sign there to represent it's greater than what's coming in here at the surface. It's going to result in a much quicker acceleration of air in the vertical, enhancement of that air in the vertical. And this is going to really lower the surface pressure. I mean, you can imagine if this vertical movement of air is stronger because we're now increasing low-level convergence, that's going to result in a lowering of the surface pressure here. Pressure is basically just the amount of weight exerted on the Earth's surface, pounds per square inch typically. And when we're accelerating the air in the vertical, we're removing air upward away from this air column, making the pressure lower and lower over time. So on the other hand, now what happens when the rate of surface convergence overtakes the ability of divergence aloft to compensate? So now we're saying that the lower level convergence is stronger. This is now stronger down here. In the low levels, the converging air is stronger than, I'm going to draw, I'm going to use these arrows. The magnitude of the arrows represent strength. So I'm going to draw shorter arrows aloft. So these arrows at the surface, the low-level convergence arrows, they're much longer. So imagine it's a vector and it has a longer, it's longer in size. That indicates a greater magnitude. So in this case, if we get low-level convergence down here at the surface is stronger than what's being removed aloft. So faster, we're adding mass down here at the low levels of the atmosphere, okay? And we're not removing the mass aloft as quickly in the upper levels. So what happens is that is going to result in an area of low pressure that weakens, and what we call that is a filling process. And low pressure systems are going to, here's the red L, that represents your low, they're going to fill, or the barometric pressure is going to rise because I have more mass coming into low levels than is being removed aloft. So therefore, I have rising pressure. This low pressure is undergoing a weakening or a filling stage. All right. In the mature phase, the upper air trough continues to deepen, and the surface flow also develops further. So we have a case, if I were to draw this out, so let's say we have an area of low pressure at the surface. Now this is on the ground, okay? And I have a feature at 500 millibars. Let's just call it a short wave at 500 millibars up here. So I'm drawing my 500 up top here. And then I have a trough. Here's your trough axis. This is 500 millibar level up here. This is my upper wave feature, that short wave trough that's supporting this surface low pressure system. In the mature phase, what's going on is that low, everything is lined up perfectly for this low pressure system at the surface to get stronger and more intense because I have an area of upper level divergence and positive vorticity advection generally out ahead of this shortwave trough, downstream of it, and that is accelerating the removal of mass aloft, that chimney effect I talked about. So I'm having greater, I'll put the plus sign up here, I have greater removal of mass aloft at 500 millibars because my shortwave trough is back to the northwest of the surface low. Now, in the mature phase, that's what happens. This is a mature system here at this point. This is where the low pressure is deepening. When I use the term deepening, I mean that low pressure at the center of this, the barometric pressure at the center of the low is actually getting lower and lower. So by the occluding phase now, let's pay attention to this last bullet. We get a closed isoheight or height contour that exists aloft, indicating that the low pressure center is lifting and the trough axis begins to pivot around this upper air center of low pressure. So now let me just go ahead and erase this. Okay, let's erase this, and I'm going to show you now what happens in the occluding phase. All right. So the occlusion phase is going to be represented by this. Okay, so now here's our surface again. I have an area of low pressure at the surface. With the occluding phase, we now have that upper level trough, which is now closed off into a complete, it's an enclosed upper low basically at this point, the occluding point, the occluding phase point. And that upper level low is directly vertically stacked above the surface low. So now my area of divergence is way out here. My upper level trough is outrunning the surface low pressure movement. And what I'm getting now is a closed upper low directly above the surface low in the occluded phase. And that's now going to result in the surface low is going to fill, the central pressure will rise, and that eventually this the whole low pressure system is going to fill from the bottom up. And you're going to see the reflection at the 500 millibar level here with a closed low. That's going to remain the longest. You will see this surface low pressure system eventually dissipate, and you'll no longer see the reflection on the surface weather analysis. But you will see, if you look at a 500 millibar chart, you will see the closed upper low remaining for quite some time after this surface low fills. This, by the way, occluded phase, usually the beginning of the occluded phase is when the storm reaches peak intensity, but then this upper level trough closes off, we have a closed height contour around it, and it tends to move quicker than the surface low. So now we have a vertically stacked system, which eventually that's going to result in a conversion from a baroclinic low to a barotropic cold core low. Here is some great graphics to kind of really see the connection between the surface pressure features and the upper levels. The upper left-hand graphic here showing an area of low pressure at the surface. See that? Here's an area of high pressure. And look at the connection. Look at the connection up here to the upper levels. If this is my 500 millibar chart, this upper level chart, directly above the surface weather systems, I generally have this low pressure is going to be supported by this shortwave upper level trough at 500 millibars. You kind of see where the axis is right here. So that surface low is going to stack back towards the northwest to the upper level low feature supporting it. Look at this, divergence. Divergence downstream of the trough axis. Now this position where the surface low is located here and the upper level divergence is above the surface low, it's helping to strengthen or deepen this surface low. So the storm's undergoing intensification at this point. But you see how that low pressure stacks back to the upper level trough. Same thing with the surface high pressure system. That is going to stack back towards the upper level ridge. Generally, this is your ridge axis at 500 millibars, a shortwave ridge. And ahead of the shortwave ridge, we have NVA, negative vorticity advection, and upper level convergence, which is going to result in sinking air motion. It's going to intensify this surface high. If you look at the graphic here on the right, just showing you within a upper air feature, upper air pattern. Generally, this U-shaped pattern here is a trough. This upside down U-shape is a ridge, and there's another trough, okay? Usually have like this pressure ridge, and then you'll have a shortwave trough. There's another shortwave trough axis. But in general, why do you get the divergence right at this location downstream of that trough axis, it's due mostly to the effect of speed divergence. And I'll get to that here at the bottom here in a moment. Typically, you get speed convergence coming out of the ridge, going into the base of the trough, and then you get speed divergence downstream of that trough axis. And so this area of upper level divergence is going to result in stormy weather and typically low pressure at the surface. This area of upper level convergence is going to result in fair weather and high pressure at the surface. Okay? And it's a repetitive cycle within the atmosphere. These short waves in general propagate through the long wave pattern, and they're very much responsible for what we see here as far as weather at the Earth's surface. Look at the chimney effect. In general, in this case, we're looking at speed divergence aloft, where I have, this is 90 knots of wind, and then I have 50 knots of wind coming into, I have more leaving this air column, more mass leaving the air column that's coming in. I got a 50 coming into a 90, so I'm losing the mass aloft at this point. That's going to favor the development of surface low pressure, low level convergence, chimney effect. If I have speed convergence, now I have the slower wind speeds out ahead at 50 knots, and then I have a 95 knot wind blowing into a 50 knot wind. That's going to result in an accumulation of mass at this point and sinking air motion and the development of high pressure at the surface. So you see how everything is linked. Atmosphere is a three-dimensional fluid. You have to look at all aspects of the atmosphere. Surface pressure features in the mid-latitudes are supported by upper-level features up at 500 millibars, up at 300 millibars at jet stream level when we get these jet streaks to move into and out of an area. That jet stream supports the development of these features as well in the lower levels of the atmosphere. Now, with the cutoff lows, that's that closed upper level low. In the occluding phase, as that surface low lifts out, that air column fills, the center of low pressure becomes aligned or stacked vertically, as I mentioned a couple slides ago, with the upper level low. So I have upper level low directly above upper level low. It's closed off completely, a height contour surrounding it like that, and I have a surface low below it. It's basically the surface low is directly in vertical alignment with the upper low. The low will then transition to a cold core barotropic low. Cold core low, remember, has the coldest temperatures towards the center. And that will display very little temperature contrast. When we go to barotropic systems, I no longer have that temperature advection. The temperature contrast is pretty much destroyed or eliminated, and that will lower my potential energy. So less divergence aloft, and the surface winds at the low pressure center are greater than the winds aloft. This causes that low level flow to pile up. Mass accumulates in the low levels of the atmosphere where that surface low is, and that assists the occlusion process in forcing that low pressure center aloft and cutting it off basically from its source of energy. That temperature contrast, that temperature gradient, that is the energy for these baroclinic systems, these mid-latitude cyclones. Overall, this effect will produce an upper level cutoff low, as I previously mentioned, and as the low pressure center continues to be forced aloft, the convergence beneath it fills the surface low, and the original surface low now exists aloft, embedded in the upper air wave, and that's what I was mentioning. If this is the surface, you may not see that reflection of a surface low anymore as it fills. You may only see a closed height contour and upper level closed low remaining. Maximum surface convergence now corresponds to the triple point of greatest potential energy, resulting in a favorable area for new cyclogenesis. I hit on what the triple point was in the last training video, but if I were to draw it out, okay, the triple point, this is a warm front here, this would be an occluded front here, and I apologize for the colors because they're not exactly in line with what the colors would be, but I'm just showing the symbology on this particular example. These are going to be the wedges. All right, so this is your cold front. All right, I'll put a C there by it. This is the warm front, so I'll put a W by that, and this is the occluded front. O. I put a letter O. Apologize. Apologize for how sloppy that looks. But this is the occluded front. That is supposed to be a letter O. Right, so the triple point is the point where all three fronts meet, right here, right in that location. That's a triple point. That is a favorable area for new cyclogenesis, the new development of a low pressure system. Consider it like a wave train, and that's really what the polar front is. It's a wave train. You have the low pressure system go through its life cycle, starting out with the initial phase to the mature phase to the occluded phase, and then you have a new low pressure system that develops and takes its place at the triple point, the area where the occluded front, warm front, and cold front meet. All right? Here is an example. I probably should have just waited a slide to show you, but just again showing you the relationship of this is at the surface here, okay, and this is the upper levels. So at this point, this is starting to close off in the upper levels. See how these black height contours are surrounding this area of low pressure at 500 millibars? So now we're having a closed off upper level low at this point. It's not quite vertically stacked yet, but it's going to catch up to the surface low, and eventually it's going to be closed right over the top of the surface low, and that's going to result in weakening or filling of the surface low, rising barometric pressure. Sometimes, though, you get the triple point travels along with its parent system, encounters an area of baroclinic instability or a jet streak with explosive cyclogenesis due to enhanced upper level divergence. The triple point serves as a breeding ground or place for new surface lows. So, for example, on this particular graphic on the right, the triple point is there. This is the most favorable area, the greatest potential energy. We still have the cold air mass behind the cold front moving in like this. We still have a warm air mass moving in like this. And if you get a new wave of low pressure to develop at the triple point, that's going to start turning these air masses inward towards each other. And you're going to have the development of a new storm system, cyclogenesis. Okay? And additionally, as this was mentioned, sometimes you get these jet streaks that blow right over the top of these things, the triple point location. And if you get one of those jet streaks where you get your upper left front or the right rear quadrants of that jet streak, that accelerated region of wind to be right over the top of this location, it can kick off a new area of upper level divergence, removal of mass aloft, and then wave development at the surface. So now I'm going to turn my attention to, these are like tips or signs for predicting cyclogenesis. The progression of surface and upper air features, you got to keep an eye on these things, both at the surface and aloft, show that certain conditions must exist for cyclogenesis to occur. Any feature that favors any kind of increased cyclonic turning of the winds is going to promote cyclogenesis. The degree of cyclonic vorticity, the location and strength of those jet streaks, and the location and strength of those shortwave upper air troughs, those divergent areas downstream of these shortwave trough axes, all help to determine whether or not cyclogenesis will occur. Positive vorticity is associated with increased cyclonic vorticity or turning of those winds and areas of upper level divergence favoring that cyclogenesis, development of a cyclone or strengthening of that cyclone. Negative vorticity, on the other hand, is associated with anticyclonic vorticity and areas of upper level convergence. That's going to favor cyclolysis. That's a weakening of the storm. So again, it goes down to, let me draw this out. Here's the surface. Here's the area of low pressure, the cyclone, middle latitudes. It really depends on what's going on aloft. If we have, let's say we have that shortwave trough to the northwest, stacked back to the northwest of the surface low, that cyclone at the surface. We have an area of upper level divergence aloft above that surface cyclone. It's going to result in a strengthening storm. On the other hand, let's go ahead and erase that. On the other hand, what happens when we get that upper level trough to exist? Actually, no, let me erase that. That's not what I wanted to do. Okay, hang on here. Bear with me here. Okay, so what happens instead if we get we got the upper level trough let's say the upper level trough is like this. So now that area PVA is removed. The effects of that PVA, or positive vorticity advection, is removed from the surface cyclone. Okay, it's not in a favorable position, and now we have an area of negative vorticity advection coming in ahead of a shortwave ridge. That is going to act to increase upper level convergence. So if I increase upper level convergence, okay, there's no way the low pressure system can survive, because what's going to happen, here's your low pressure at the surface, here's your converging air at the surface, okay? So if I have upper level convergence, I have air meeting the upper levels of the atmosphere. As it meets, it's going to want to sink. That's not what low pressures want. Low pressure wants the air to rise. So now as the air sinks, if my upper level convergence is occurring aloft over the low pressure at the surface, my air sinking is increasing my central surface pressure here, and it's going to cause a weakening or a process known as cyclogenesis to occur. You have convergence in the low levels, that's adding mass. You have upper level convergence at about 500 millibars in the mid levels of the atmosphere, that's adding mass. So if you add mass to the whole entire column like this, it's going to kill that low pressure system. You're going to have sinking air motion, which is going to cause rising barometric pressure. And that low pressure is going to weaken. Hopefully that makes sense. Other considerations for predicting cyclogenesis: the temperature difference in the lower levels. That is huge. It serves as a potential energy for mid-latitude cyclones. Patterns of thermal or temperature advection, particularly at 850 millibar level. That's at that 5,000 foot level above the ground. That also helps to determine potential for cyclogenesis. So at 850, what you want is your height contours. Let me see, just draw my hair. Imagine these solid red lines are height contours at 850. So what you want is some type of crossing of these isotherms with these height contours. Okay. You want that crossing, you want that perpendicular relationship between these dashed red lines, the isotherms, lines of equal temperature, and these height contours, the solid red line. So let's say this is 0 Celsius. This particular isotherm everywhere along this point is 0 Celsius. Let's say this is negative 5 Celsius back here at this isotherm. Let's keep going here. This is negative 10 Celsius. Okay, so that'd be negative 10 C right here. And then let's just say the upper level winds are blowing like this. Okay. Remember, the upper level winds above the planetary boundary layer, they generally blow parallel to the height contours. There's no friction at this altitude, 500 millibars. And so, if you're at a location like this, right here, the winds are going to blow colder air. There's a advection here. There's a temperature advection. Colder air is going to blow into your location. If you're right here, okay, that wind's going to blow these colder temperatures into your area. And this was, let's say this is, we'll go back to our example here. Let's say this is 850 millibars. And again, my isotherms are perpendicular to the height contours at 850 millibars. That's going to result in a strengthening of a storm system. It serves as that potential energy. Contrasting air masses is really the key. The larger you get the difference in air masses, the greater the potential energy available, with higher probability for cyclogenesis. And that's why we see such strong mid-latitude cyclones in the winter season, because we have such great temperature contrast over shorter distances. Additionally, moisture. You've got to take a look at moisture. It cannot be overlooked, as moisture represents a source of potential energy. Also, it represents a form of instability moisture in the form of latent heat of condensation. So remember, latent heat of condensation is the conversion of a water vapor, that invisible gas water vapor, to a liquid. And as that vapor transitions to a liquid, it releases heat to the surrounding atmosphere. And that is going to further destabilize things. That addition of heat can enhance the potential energy and also cause intensification of existing cyclones. And, I'm thinking about wintertime off the U.S. East Coast. We're talking about an area of low pressure over a Gulf Stream, the Gulf Stream current. That low-level heat and moisture from that Gulf Stream can really cause some major bombing of cyclones off the East Coast in winter. Identify moisture potential of the air masses. That's important. Those originating from or retaining access to the ocean or the Gulf of Mexico have enough moisture to fuel the cyclogenesis. Here's some examples in summary of both thermal and vorticity advection. On the left here, I am showing, let me go ahead and go back to my pointer. On the left here, I'm showing you an example of vorticity advection. This is actually called a vorticity couplet. This is your shortwave trough axis. By the way, this X at the center, this represents your vorticity maximum, your highest vorticity value associated with this couplet. Imagine this is your shortwave trough at 500 millibars. These solid black lines represent your height contours, and these purple dashed lines represent your isopleths of vorticity, or lines of equal vorticity values. So, again, the winds are generally blowing west to east in the mid latitudes, parallel to these black solid lines of height contours. So let me get my drawing tool back out. Right, so let's analyze a location, let's say right here, right in this location. The winds are going to blow parallel to the height contours like this. They're going to follow from west to east. That wind is going to follow, be parallel to the height contours. So right now I have a vorticity value of 16 to my west, a value of 18 to my west, 20 and 22. So the wind is going to blow these higher values of vorticity into my area. That is positive vorticity advection. The wind is blowing higher values of vorticity into my area. Okay, at this point right here. So I'd expect positive vorticity advection, PVA, out ahead of my shortwave trough axis. PVA is associated with upper level divergence, removal of mass aloft, and rising air motion in the atmosphere. Rising air motion is associated with clouds and precipitation. Now, behind the shortwave trough axis, now let's analyze what's happening at this point, right here. I'll do a big circle, or I'll just make it right here, a big red dot. So now my winds are blowing parallel to my height contours. They're geostrophic in nature. There's no friction at 500 millibars or 18,000 feet. And in general, now I have lower vorticity values moving towards my location. If I'm here, behind the shortwave trough axis, lower areas of vorticity is basically going to result in what's called negative vorticity advection, NVA, and as the air sinks in this particular area associated with upper level convergence and negative vorticity advection, or NVA, I'm going to have fair weather. So see, I even have weather descriptors here. Now this is again known as a vorticity couplet. This is a shortwave trough relationship to vorticity. PVA downstream of the shortwave trough axis, NVA upstream of it. Now if I were to have an upper level ridge, okay, let's say now this is an upper level ridge, the sawtooth line represents my ridge, here's my height contour, okay. Out ahead of an upper level ridge, we just flipped the vorticity advection. So ahead of shortwave ridges, I now have NVA, negative vorticity advection, and then behind these shortwave ridge axes, I have positive vorticity advection. Okay? So it's just the vorticity couplet is flipped between shortwave troughs, which I'm showing here. This one's a shortwave trough, and then these shortwave ridges. If you look at the upper level charts here, and we look at 1,000 to 500 millibar thickness chart, in this particular chart, we're analyzing for temperature advection. All right, we're looking to see if the thickness lines are perpendicular to these the isobars, lines of equal surface barometric pressure. If they are perpendicular, the thickness lines to these isobars, then we have some sort of temperature advection occurring. And then you'd want to analyze the pressure system features. With low pressure, generally has counterclockwise winds in the northern hemisphere. High pressure is generally going to have clockwise flowing winds around it in the northern hemisphere, okay? So in general, here's my clockwise flow. 1,000 to 500 millibar thickness chart, very handy tool, and I talked about that in my How to Read and Interpret the Basic Weather Charts video, so take a look at that one. But in general, I've got upper level features. I have these thickness relationship to temperature. Lower the thickness, the colder the temperature, the higher the thickness, the warmer the temperature. And so we have these relationships of colder air moving in behind troughs, warmer air advection ahead of troughs in the northern hemisphere. And then finally, we can look at just a regular chart down here at the bottom right. This is a upper level low. This is an upper level high out here over the western U.S. In general, you can see where your trough axis is located over the central U.S., and then you have a ridge axis up the eastern seaboard. In areas of positive and negative vorticity, you'd expect PVA out ahead of the shortwave trough, NVA sinking air behind it, and out ahead of the ridge axis, you'd expect NVA over here off the east coast. And this is all the vorticity couplets again. Additional signs for predicting cyclogenesis at the surface, you want to look for places where you have contrasting air masses meeting. The greater that temperature contrast across fronts, the greater the probability for cyclogenesis. If cyclonic shear exists along the boundaries, these frontal boundaries, watch for surface wave development. And if you get a tight pressure gradient that exists, that means I have a tight packing of my isobars, the lines of equibarometric pressure at the surface. If that pressure gradient is very tight, tightly packed isobars expect wave development. We got a lot of potential energy in this case. Check the temperature advection patterns at both 850 millibars, that's 5,000 feet above the ground, and that 700 millibar chart at 10,000 feet above the ground. Check that temperature advection patterns between the surface up to 850 up to 700 millibars. One thing I wanted to tell you is the winds, how they change with height matters. If I were to look at a thermodynamics QT diagram, and let's say my winds are going from, let's say they're blowing, I'm not going to use wind barbs here, I'm just going to make this really simplistic. So let's say at the surface my winds are from the southwest. And then up at the mid-levels of the atmosphere, let's say 700 millibars are from the west, and then they're from the northwest at, let's say, 500 millibars. So surface winds from the southwest, 500 millibars are from the west, at 500 millibars from the northwest. Whenever the winds change direction with height like this, that's called a veering pattern. A veering pattern with winds with height indicates warmer air advection. Okay, veering winds with height is warm air advection. That's just abbreviated WAA. If I look at a thermodynamic or a SQT diagram, and now I see my winds are doing this. Let's say my winds are from the northwest of the surface, and they're from the southwest at 700 millibars, and then they're from the southeast at 500 millibars. So now I have a wind going from southwest, northwest, starting at northwest, and then going southwest with height, and then going southeast. This is an example of cold air advection, or a backing wind with height. This is going to represent colder air advection, colder air moving in. Whenever my winds with height back, right? And really, all you got to think about with veering winds versus backing winds, veering winds are going to work in a clockwise manner with height, similar to the hands of a clock. Whereas cold air advection and backing winds are going to act opposite of the hands of a clock. Okay? So you want to check the temperature advection patterns. And then strong warm air advection occurring in advance of deep cold air advection, that's going to set the stage for increased baroclinicity, temperature contrast that fuels cyclone development. Additionally, the developing storm requires moisture to produce significant weather. You got to have that lift, but you also, most importantly, have to have enough moisture to be added or to be lifted in the atmosphere. If you have a very dry air mass and lack of moisture, that's going to be a limiting factor for cyclogenesis. So you want to start with the warm air mass. You want to check for moisture source upstream. For example, the Gulf of Mexico or ocean surfaces that can be tapped into to provide that moisture, that fuel to the developing storm system. You also want to look at dew points, surface dew points within the air mass to verify the moisture content. Additionally, you want to look at the forecast motion of the surface low. Weak surface disturbances can tap into upper air features that support cyclogenesis by moving to the left of their expected track. And this may put that developing cyclone at the surface beneath an area or region of upper level divergence into a more favorable position for strengthening. Conversely, deviation of a track to the right is going to decrease the upper air divergence, and that will discourage further development. So just pay attention to the track of that surface low. Pay attention to upper air features. Sometimes you get these minor short waves that can exist at 700 millibars or 10,000 feet, which really don't show up very well on the model data, but they can have a huge bearing on the type of weather you get. Additionally, note the strength of fronts to help ID the cyclone stage of development and whether or not the storm is intense. Stronger the fronts, the greater the temperature contrast across these fronts, the greater the potential for an intensifying storm system. Now, once you lose that temperature contrast across the fronts, then you know most likely that storm is decreasing in intensity or weakening. The degree of that thermal or temperature contrast between the air masses is huge for fueling cyclogenesis. Weak fronts indicate very little thermal or temperature contrast and weak cyclones, while much stronger fronts feature greater temperature differences, closely packed isotherms, lines of equal temperature, helping to identify more powerful cyclones. At 700 millibars or 10,000 feet, notice the packing and number of isotherms. Close packing parallel to fronts is going to indicate strong thermal or temperature gradients, while less packing and the intersection of isotherms with fronts are going to indicate weak and diffuse frontal boundaries. So even up at 10,000 feet, you want to notice how that relationship is of the isotherms, lines of equal temperature. If they're generally close together, related to each other, they're very closely packed, parallel to the front, that indicates that strong thermal gradient or that increased potential energy for the cyclone. Less packing, or let's say those isotherms are further apart from each other, an intersection of those isotherms with the front, that's going to indicate a weak or diffuse frontal boundary. And finally, check the 700 millibar iso heights, or those height contours at 10,000 feet, 700 millibars, of identifying fast or slow moving fronts. Iso heights that are nearly perpendicular, those height contours that are perpendicular to the front, indicate a fast moving front. And with fast moving fronts, airflow behind the front impacts the front directly, imparting its strength squarely to that frontal surface. Whereas iso heights or height contours that barely cross or are parallel to the front indicate very little push and slower moving fronts. Here are some example charts. Let's take a look first here on the graphic on the left. Let me go and get my pointer back out. All right, on the left here, I'm showing you, this looks to be a surface chart. Yeah, this is a surface chart. Surface weather analysis with fronts. Red L's are low pressure systems at the surface. Blue H, high pressure systems at the surface. These orange solid lines are isotherms, lines of equal temperature. That would be right here. So I'm not showing you isobars on this particular map. I'm showing you lines of equal temperature, these solid, I call them orange, but they actually look more red. And they're in 10 degree increments. So for example, everywhere along this red line has a temperature of 40 degrees Fahrenheit. Everywhere along this line has a temperature of 30 degrees Fahrenheit. Everywhere along this line is 20 degrees Fahrenheit, and so on. So notice the packing of the isotherms in relation to this frontal boundary. See how much more tightly packed they are from eastern Iowa into northwestern Illinois. See this right here, southern Wisconsin? This is an area where we have a stronger frontal system. We have greater contrast between the temperatures, a stronger temperature gradient over a shorter horizontal distance. If I were to drive from western Illinois to central Iowa, my temperature is basically going from about 30 degrees Fahrenheit to 10 degrees Fahrenheit in just this short driving distance. That might be maybe 200 miles distance, and I have a major change in temperature. That indicates plenty of potential energy for these waves of low pressure to work with. On the right-hand side, I'm showing you an example of this is a surface weather chart as well. A very intense cyclone off the eastern seaboard. Solid lines, the solid brown lines are the isobars, lines of equal barometric pressure. Notice how tightly packed these isobars are in relation to each other from Indiana all the way to the eastern seaboard, up into New England. This is going to indicate a lot of potential energy. This is a very intense system in the atmosphere, And you're also going to have very, very strong winds. And you see how the green area is, this green shading? That's your areas of precipitation on the backside of this monster low pressure system. By the way, this low pressure system was Hurricane Sandy. And many of you remember that one, especially if you live anywhere from Virginia and northeastward to New Jersey, New York City, Long Island. Yeah, this was obviously a very intense system, Sandy. Here, if we take a look, we're looking at a chart here that shows lines of equal dew point temperature. These solid green lines represent what are known as Isotroso Therms. And you can see the intervals are 10 degrees Fahrenheit between each Isotroso Therm. What I'm doing here is the tightest packing, I just want to show you that, is located right over this in this red circular area. So we got a very strong, in this case we have a very sharp moisture gradient. I'm going from dew points at the surface of 60 degrees down around the very far western tip of Kentucky. And by the time I get up into Iowa, my dew point temperature has dropped off rapidly, 40 degrees. So there's a lot of moisture available. You see the 70-degree isotroso therm creeping up into Tennessee and North Carolina. So we have very strong moisture gradients. This is another sign of an intense system, in addition to those stronger temperature gradients. Right, now in the upper atmosphere, to conclude today's training, I'm going to talk about how you predict cyclogenesis looking at the upper atmosphere. So if you look at that 500 millibar chart, 18,000 feet, you want to look for those short waves and do their locations correspond to the boundaries, those frontal boundaries at the surface, between dissimilar air masses. Short waves are faster moving, and they're most likely going to be associated with those jet streaks at 300 millibars. The accelerated regions of wind in the jet stream axis or the core, those jet streaks are going to help move those short waves along rather quickly. Additionally, in the upper levels, you want to check for areas of upper air divergence, how that supports development of the surface low, and then check for those areas of convergence in the upper levels as well. Match them with surface features. Do the upper air divergence areas correspond to a favorable position aloft above that surface low, or do I have upper air convergence coming in aloft over a surface low, which is going to weaken that surface low? You need to look at that vorticity couplet as well, with PVA being associated with the upper air divergence downstream of the shortwave trough axis, and NVA, upper level convergence, behind the shortwave trough axis. See how that vorticity and upper air divergence and convergence, how it corresponds aloft above those surface features. I want to look at a 700 and a 500 millibar chart to see where that shortwave trough axis is and where those areas of upper air divergence and convergence, as well as vorticity advection, is occurring. You also want to consult the 300 millibar chart for that jet stream location. This jet becomes stronger, faster, and lower in winter. The polar front jet we're talking about, due to seasonal intrusion of polar air southward. You want to locate any jet streaks again within the polar jet axis, and then locate subtropical jet too if one is present. Sometimes what you get is a merging of favorable quadrants of jet streaks associated with both the polar front jet and the subtropical jet. It's happened before, definitely off the eastern seaboard of the U.S. That can lead to intense cyclogenesis. Some historic storms have occurred because of this configuration of jet streaks between the subtropical jet and the polar front jet. Additionally, you want to note the intensity and curvature of the jet. Strong cyclonically curved wind flow associated with those jet streams will transfer angular momentum downstream in the form of positive vorticity advection. So that's going a more tightly curved and intense jet. When I mean intense, I'm talking about very fast and strong wind speeds in a cyclonically curved jet. That's going to, again, transfer that momentum downward, and that is going to increase your levels of vorticity, positive vorticity values. High vorticity along with strong PVA, that is a magical combination that favors upward vertical motion and cyclogenesis, low pressure system development, or intensification of an existing surface cyclone. And that speed of the jet streak really does matter. That affects the divergence aloft. Stronger jet streaks can foster low-level convergence at the surface, producing a very effective chimney effect. Excellent exhaust mechanism, removal of mass aloft over low-level convergence. You also want to look to the right of the entry and left of exit regions of that jet streak for the favorable quadrants for upper-level divergence and possible surface cyclogenesis. Also check for the upper-level cold air advection. Look at 850 millibar charts and higher. Do you have cold air aloft, which is encouraging cyclogenesis by lowering those upper-level height contours? And then I believe this is the last slide here, yes. Just want to end tonight's training by again showing you the relationship. There's many moving pieces in the upper-level pattern that correspond to cyclogenesis or cyclolysis. The graphic here on the left is showing a long wave ridge at this point over the western U.S., a very deep long wave trough downstream of that long wave ridge. And within this long wave trough, we have little upper air disturbances, pockets of energy associated with positive vorticity in these short wave troughs that are rotating through the long wave pattern. They're following these upper level winds parallel to the height contours, blowing them in from the upper Midwest into the mid-Atlantic. So I would be very interested in looking at a 300 millibar chart to match up with this 500 millibar chart, just to see where the jet streaks are located in relation to these short waves. We know PVA exists ahead of the shortwave trough axis, so if I were to draw out, just looking at a 500 millibar chart, where would I see favorable upward vertical motion, possible precipitation, as well as clouds? It would be in this area here, ahead of the shortwave trough axis, right along the Carolinas, Virginia, up into Pennsylvania. Now, behind the shortwave trough axis, I would expect sinking air motion over Ohio, Indiana, Illinois, Missouri, Arkansas, West Tennessee. All right? And so, generally, this is what I'm looking for. Now, I don't have a 300 millibar chart on here to kind of look to see where the jet streaks are located. If I have an accelerated jet streak in this location here, and I divide it up into 4 quadrants, the left front quadrant and the right rear quadrant are going to be the most favorable locations for rising air and upper level divergence. If this was occurring at 300 millibars above this 500 millibar level, that is only going to enhance the removal of mass aloft and most likely result in a more intense cyclone at the surface. If we look at the jet streak and the jet level, this is an example of the jet streak again. The yellow lines here represent your lines of equal wind speed, isotax, these yellow lines here, okay? Notice how it's an oval shape. Generally, again, showing you the areas that are favorable for upward vertical motion and downward vertical motion associated with these jet max or jet streaks. Generally, you have a positive vorticity advection maximum in the left front quadrant and the right rear quadrant. This is going to be your divergence in the upper left and the right rear quadrants of the jet streak. Let me draw it out. Just showing you one more time. If I were to split this jet streak right down the middle, okay, the left front, which is over in this location, and the right rear are favorable areas for upward vertical motion, clouds, and precipitation, and storm development. Whereas the right front and the left rear quadrants are associated with negative vorticity advection maximums and upper level convergence and downward sinking motion. So if my location coincides with these shortwave troughs and upper level divergence, I would expect to see low pressure in the left front or the right rear quadrant of the jet streaks. The right front would be associated with high pressure and nice weather, as well as the left rear. Okay. All right, that wraps up the training tonight. I appreciate you subscribing to the Spot on Weather YouTube channel. Getting some great feedback from everybody out there. Just got a comment tonight in LinkedIn. Aaron had reached out to me saying thank you so much for these training videos because it really helps him understand how the weather works more efficiently. And so you're more than welcome, Aaron. I definitely appreciate the kind words that you sent to me earlier today. And again, I hope everybody's enjoying this How the Weather Works training series. Again, I got many more videos to follow as we move through We're getting close to June, believe it or not. Time is moving quickly. But I do have more videos I will be sharing on this channel. So stay tuned for more information. I'm going to close it out and wrap it up. And thank you again for your attention and taking the time, most importantly, out of your busy lives, your busy schedules, to listen to this training. All right, if you have any feedback for me, please feel free to leave a comment on the video here on YouTube, or feel free to give me an email at eulermatthew4@gmail.com. Okay? Take care, everybody. Until the next training session, take care, and God bless everyone.